All right, everybody. In this video, we are going to move into the last section of this material in Calculus 2. It's also the last section we do in Chapter 8, which is called Probability. I'm going to show y'all how integration can be used to do some basic probability problems. One thing to note about this section is that when you're going through the homework and such, some of the problems are going to ask you for exact answers, and then some of them are going to ask for the actual percentage or probability answer. So just keep in mind that for your test that you don't get a calculator on, I'm never going to ask you for the decimal, but I do know that some of the homework problems will ask. So I'm going to give you the decimal answers today as we're going through so you can kind of see what they're expecting. All right, so I got a little bit of talking to do. So if at any point you need to pause the video to catch up, that's fine. But I got to talk through a couple slides before we get to our first problem. So calculus can be used to find probabilities if we consider the probability as the area under the curve between A and B. Well, like we know, that's what integration is. Integrating the area under a curve is how we'll do this. We can use a probability density function to evaluate these probabilities. So the first thing that we can say is that the probability of something happening between an A time and a B time can be found by just integrating from A to B f of x dx. Now the challenge is going to be is what is this f of x going to be? That's what we're going to talk about on the next slide. It's not just going to be a regular function. So as you may know, if you've had a stats class or maybe you don't know, all probabilities have to be measured between the values of 0 and 1 because 0 probability means it would never happen. A 1 probability means that there's 100% chance of it happening. So you should always get values between 0 and 1. So based on that definition, if you were to integrate from negative infinity to infinity of a probability density function, then that is guaranteed to be 1 because if you check the probability from the beginning of time to the end of time, it is guaranteed to happen, and therefore that would give you a value of 1. All right. Couple of other things from probability that we need to know. The mean. If you're trying to find the average of a probability density function, so we know that the average occurs somewhere between the beginning of time and the end of time. So we can define the mean, which is also the Greek letter mu, lowercase mu, is the integral from negative infinity to infinity of x times the probability density function. Now, all these formulas that we've been doing so far have been totally reliant on knowing what the probability density function is. Now, there's a bunch of different ways to do it. We're going to focus on the easier one in this section. That way, it's the easiest to work through. We're going to work with a special case called the exponential density function. The reason that we define the exponential density function is because mu is a little bit easier to find in this case. Mu is defined as the ratio of 1 over c, and then you'll use that formula to then define your f of t. Now, this f of t is what's been inside all of these formulas that I've been showing you. But there's a slight problem. F of t is defined as the probability is 0 if time is less than 0. Now, that kind of makes sense. If anything is less than 0, it's impossible to work. But if we let t be greater than or equal to 0, it's defined as c times e to the negative ct. But what is c? Well, c comes from this formula for mu. If you were to rearrange this to get c by itself, we could say that c is defined as 1 over the average or the mean of the density function. So how does that change our problem? Well, that changes your lower parameter of this piecewise function to be 1 over mu times e to the 1 over mu times t. This will be your exponential density function anytime t is greater than or equal to 0. That is the most important thing on here. This is the formula we will need to solve every problem that we do today. All right, and then outside of mean, the only other thing that we're going to cover today is the median. So if you're trying to figure out what the median of any probability density function is, so the median is the exact midway point where half of the data is above it and half of the data is below it. You can find that by integrating from m to infinity of the density function and setting it equal to 1/2. And your job will be, how do you find that value of m, which is the lower parameter of the integral? All right. Now, somebody usually also asks me, is it possible to also do it from 0 to m? It is. Or, since we're going to be doing exponential density functions, we could integrate from 0 to m of f of x dx and set that equal to 1/2. I usually don't go about doing it this way, not saying it's wrong, but usually plugging infinity into stuff makes it go a little bit nicer with all these extra fractions. Trying to plug 0 into these fractions may get a little bit ugly and a little bit more critical thinking. So I'm probably not going to do it this way. I'm going to stick to the more traditional format instead. All right, so now that we have all the information covered, let's work 4 or 5 problems. I think there's 4 or 5. There's 3, but some of them have multiple parts of how we can use the probability density functions. Let me read this entire problem and then we'll break it down. A type of light bulb is labeled as having an average lifetime of 1,000 hours. It is reasonable to model the probability of failure by an exponential density function with the mean equal to 1,000. Use this model to find the probability of failure within the first 200 hours and the probability of it burning more than 800 hours. Also, what is the median lifetime of these light bulbs? All right, so essentially what this problem reads as is that or what the manufacturer is claiming is that their light bulbs last an average of 1,000 hours. We're going to figure out how accurate that actually is by using an exponential density function. So since mu was defined as 1,000, it is very easy to see that we could find c, which is equal to 1 over mu, to be 1 over 1,000. That then allows us to express our exponential density function, remember, is equal to your c value, which is 1 over 1,000 times e to the negative ct. So this would be negative 1 over 1,000 times t. This is the function we're going to use to solve all 3 parts of this question. So beginning with part A, what is the probability of failure within the first 200 hours? So we're trying to figure out what's the probability that the light bulb will only last between 0 and 200 hours. So this allows us to set it up as an integration problem. We are going to integrate, and your parameters are what you're checking your probability to be. That would be 0 to 200 of the exponential density function. 1 over 1,000 e to the negative 1 over 1,000 t. We're going to integrate this with respect to t. Now, one of the neat things here is that these will always be u sub problems, and you're going to always let u equal the power of e. So if u equals that power, I can say du equals negative 1 over 1,000 dt, which will be a direct substitution other than you having to pull a negative out front. So when I substitute this u sub in, I would pull that extra negative in front of the integral. I must change my parameters. So if I plug the 0 and 200 in for t, my new parameters would be from 0 to negative 1/5 e to the u du. Since my parameters are technically backwards, I can flip those over and I can write this as the integral from negative 1/5 to 0 of e to the u du, and that cancels the extra negative out front. Will that always happen? No, but it's something to keep in mind. We can now integrate this as e to the u evaluated from negative 1/5 to 0, which will be equal to e to the 0, which is 1, minus e to the negative 1/5. And as far as an exact answer goes, that is the best you're going to be able to do without a calculator. And that's what I would be looking for on your test. Now, on your homework, if they actually ask you for the probability here, just round to whatever they want to and just get a calculator out. This comes out to be, I did it a little bit earlier before I made this video, I got 0.181 as my probability, which for those who are not statistically inclined, that means that we are claiming that 18.1% of the light bulbs will die in the first 200 hours. That's a lot. That's almost a fifth of them. All right, so now moving to part B. Part B says, what's the probability of it burning more than 800 hours? Now, we don't know a maximum here, so to make this a little bit easier, I'm just going to say what's the probability that X will be greater than or equal to 800. So setting up this density function integration, we will integrate from 800, and since we don't know an ending time, we'll just call that infinity. And then you're going to have the exact same density function inside of your integral. Now, why is that good? Because it's the exact same technique of integration, just with different parameters. So you can do the same, you can use the exact same u submaterial as we did up here. So when I do that, that allows me to factor a negative out front again. If I plug 800 into this, negative 800 over 1,000 is negative 4/5. And then if you plug infinity into this, you will get negative infinity of e to the u du. Once again, those are backwards, so if you would like to flip them over, you can. I will flip it over into negative infinity to the negative 4/5 of e to the u du, which allows me to cancel the negative that's out front. And now it works the exact same way. This integrates into e to the u from negative infinity to negative 4/5, which will be equal to e to the negative 4/5 minus e to the negative infinity. Now, e to the negative infinity just goes to 0, so you get a final exact answer as e to the negative 4/5. That is the exact probability of a light bulb lasting more than 800 hours. Now, if they ask you for a decimal approximation, when I did it earlier, I got 0.449, which means only about 45% of the light bulbs actually last more than 800 hours, even though they're claiming that the average is 1,000. That doesn't make sense. Well, that's where companies get you. So what we want to do is we added this part C in. We now want to figure out what's the median lifetime of these light bulbs. So if you were to put half of them above and half of them below, what's that middle spot that we can find that probably is closer to the actual mean? So in order to do median, this is not a probability problem. You will have to actually integrate from m to infinity of your exponential density function. So 1 over 1,000 e to the negative 1 over 1,000 t dt. Once again, it's the exact same u substitution for the third time. That's the nice thing about these multi-part questions. So if I do the exact same u substitution, this would be the negative of the integral. Now you got to change your parameters again. So it would be negative m over 1,000, and then to the negative infinity of e to the u du. I know negative infinity has to be the smallest number, so I can flip my parameters again and go negative infinity to negative m over 1,000 of e to the u du. Integrate that, so this is e to the u evaluated from negative infinity to negative m over 1,000. All right, so when I plug my upper parameter in, you get e to the negative m over 1,000 minus e to the negative infinity, which we already saw that e to the negative infinity is 0. So you get e to the negative m over 1,000. Now, our goal is to solve for that m value. For it to be the median, That means E to the negative M over 1,000 must equal 1/2. What value of M makes this equal 1/2 or 0.5? All right, take the natural log of both sides, which will give you negative M over 1,000 equals the natural log of 1/2. Then I can multiply both sides of the equation by negative 1,000. This gives me that M is equal to negative 1,000 times the natural log of 1/2. And that is your exact answer. That's the best you're going to get as far as exact answers go. Now for your homework, if they want the approximate answer, when you type this in, you should get 693.1 hours, which is nowhere near the 1,000 hours that they're claiming. So over half of the light bulbs actually die within the first, let's say, 700-ish hours. So a little bit of false advertising there, which we use calculus to verify. So that is our first example of using an exponential density function. All right, so let's do kind of the same idea. I just want to kind of show you some different variations. So example number 2. The online retailer determines that the average time for credit card transactions to be approved is 1.6 seconds. That's pretty quick. So you swipe that credit card, you should be approved or declined in 1.6 seconds. So my first question is, find the probability that a customer waits less than a second for credit card approval. Now, similar to the last problem, we've got to find a little bit of information. Since mu is claimed to be 1.6, that means that for C, that would be 1 over 1.6, and therefore that applies f of t to be 1 over 1.6 e to the negative 1 over 1.6 t. All right, so now we know all that. Solving part A. What's the probability you wait less than a second? So that would be the probability that x falls between 0 and 1, because it can't take less than 0 seconds for credit card approval. That doesn't make sense. So this would be equal to the integral from 0 to 1 of my exponential density function, 1 over 1.6 e to the negative 1 over 1.6 t dt. And you're going to set up the exact same type of u sub that you did on the last problem, where I'm going to let u be the power of e. So du just becomes negative 1 over 1.6 dt, and that becomes a direct substitution. Now you do have to change your parameters. If I plug 0 in, you will still get 0. If I plug 1 in, you will get negative 1 over 1.6. You pick up an extra negative out front because of the negative in the du term, and then you just get e to the u du. And you're starting to hopefully notice a pattern of how a lot of these work. You can flip your parameters over, and we will integrate from negative 1 over 1.6 to 0 of just e to the u du. So that integrates pretty nicely into e to the u, evaluated from negative 1 over 1.6 to 0. And this will equal e to the 0, which is 1, minus e to the negative 1 over 1.6. And that is your exact answer for how long it takes, or what's the probability that a customer waits less than 1 second. Now, as a decimal, that is approximately, what did I get earlier? 0.465. So about 46.5% of customers should be waiting less than a second for credit card approval. All right, so let's check on the other end. What if you want to find the probability that a customer waits more than 3 seconds, which means, if that's that much higher than the average, maybe there's a chance your card's going to decline. So if I'm doing more than 3 seconds, that means I'm looking for the probability that x is greater than 3, which I could set up as the integral from 0 to 3 of the exact same exponential density function. The good thing is that it's the exact same U substitution, except you're going to have some different parameters. This would become the negative integral from 0 to negative 3 over 1.6 when I change my parameters, e to the u du. You can flip your parameters again to make this negative 3 over 1.6 to 0 of e to the u du. So that integrates into e to the u, evaluated from negative 3 over 1.6 to 0, which will give me an answer of, let's see, e to the 0 is going to end up being, oh, sorry, why am I doing 0? I apologize, guys. I messed that up. I don't know why I did 0 to 3. I meant to do 3 to infinity. So apologize for the last minute of the video. I totally messed that up. I was not paying attention. I was mimicking the first one, which is not it. I should be going from 3 to infinity. So that'd be 3 to infinity. So I'll go over this again. When you change your parameters, you will get negative 3 over 1.6 raised to and the upper parameter is negative infinity. You would still flip them over because negative infinity is the lower parameter. And then you would evaluate from negative infinity to negative 3 over 1.6. My apologies, everybody, for watching the video. I didn't mean to do that. That was a simple mistake. So plugging your parameters in, you will get e to the negative 3 over 1.6 minus e to the negative infinity, which we saw earlier is equal to 0. So you get a final exact answer of e to the negative 3 over 1.6, which is approximately 0.153. So only a little over 15% of customers have to wait more than 3 seconds for credit card approval. All right, now there is a part C on the next slide, so let's jump to that. So same problem. What is the little different question? What is the minimum approval time for the slowest 5% of transactions? So if you're looking for the slowest 5%, so these are the ones that take the longest to finally get approval. What this is asking you here is, what is the probability for X to be greater than something? Now, we don't know what this number is. We need to find it. So let's just call it a letter. Let's call it B. I want to know what is the probability for X to be greater than or equal to B. This needs to equal 5%, which we can represent as a decimal being 0.05. So I need to figure out what B value makes this statement true. Now here's where you can kind of be nice. Notice this, and notice what we did back here on part B. We just did a very similar formula, and we found out that when we did the probability of X being bigger than 3, that 3 was just the numerator of the E part of the exponential density function. So what we could actually say without having to work this out is that this is going to end up being E to the negative B over 1.6. Now you can go through the integration technique again, but you should get the exact same result. And I know that this should equal 0.05. There's a way you can save yourself a little bit of time in the process. All right, so take the natural log of both sides and you get negative B over 1.6 equals the natural log of 0.05. I'm going to multiply both sides by negative 1.6. That's going to end up saying that B is equal to negative 1.6 times the natural log of 0.05. And that is your exact answer for what the approval time would be to get the slowest 5% of transactions. Now, if you type that into your calculator, you should get about 4.79 seconds. So that means that only the slowest 5% will take 4.79 seconds to get approved. All right, let me do just one more. A lot of these work pretty much the same way, so I'm not going to do a gazillion. So let's just do one more to wrap up this video. So we got an A and a B, and then C's on the next slide. So suppose the average waiting time for a customer's call to be answered by a company representative is 5 minutes. So question A, find the probability that a call is answered during the first minute. That's pretty quick. All right, so if the average is 5, how often does your call get answered in the first minute? Well, if they're claiming the average to be 5, well, that means that our C value would be 1/5, and our exponential density function would be 1/5 e to the negative 1/5 t. All right, so if we're finding the probability that it's answered during the first minute, that would be the probability between 0 and 1 minute happening. So this would be equal to the integral from 0 to 1 of 1/5 e to the negative 1/5 t dt, which is going to be another similar u sub. So this one's a little bit different, so I'll actually write it. U will be negative 1/5 t, and du would be negative 1/5 dt. That is, once again, a direct substitution that you can plug in, and don't forget to change your parameters. This would be the negative integral from 0 to negative 1/5 when I change my parameters of e to the u du, which can be flipped around and integrate from negative 1/5 to 0 of e to the u du. So this would be e to the u evaluated from negative 1/5 to 0, which is equal to e to the 0 is 1 minus e to the negative 1/5. And this is your exact answer. And I believe, just a coincidence here, this is actually a number we saw earlier. It is. We saw this a little bit earlier. I didn't mean for that to happen, but that's okay. That is approximately 0.181%. So you see, same idea, just got to use your numbers that are given in your problem. All right, so a little bit different here. So we're claiming this 5-minute average. So let's just check the average for what it's worth. Find the probability that a customer waits more than the 5 minutes to be answered. So if I'm working that means I'm testing what is the probability that x is greater than 5. Well, this would be equal to the integral from 5 to infinity, I won't screw it up this time, of 1/5 e to the negative 1/5 t dt. So the same exponential density function. If you go through the process of doing the same u substitution, you just need to change your parameters this time. This would be the negative integral, and that actually will be from negative 1 to negative infinity of e to the u du. Flipping your parameters around will give you the integral from negative infinity to negative 1 of e to the u du. That integrates into e to the u that we're going to evaluate on the parameters on the next step. And this will become e to the negative 1 minus e to the negative infinity, which we have seen numerous times now that is equal to 0. And your final answer would be e to the negative 1 as an exact answer, which is approximately 0.368. So that means that almost 37% of customers will actually wait longer than the average that they're claiming. All right, and we did this a little bit earlier, but I want to do it one more time just so you have a second one in your notes. Finding the median. So can we find maybe a better true average for what it should be here? All right. So suppose the average, same instructions. What's the median waiting time for the phone call to be answered? So what we're going to actually do is we need to set up the integral from m to infinity of my probability, or I guess exponential density function here. Oh, let me write the same I've been writing. Sorry. So negative 1/5 t and then dt. You would use the same exact u sub from the previous problem, which would cause this to be the negative integral of negative m over 5 to the negative infinity of e to the u du. Flip your parameters again. So this is the integral from negative infinity to negative m over 5 of e to the u du. All right, integrate that, and you get e to the u evaluated from negative infinity to negative m over 5, which is e to the negative m over 5 minus e to the negative infinity. Well, for the fifth or sixth time just in this video, that's going to go to 0, and you get e to the negative m over 5. We want that to be our median, that m value, which means I need to take this e value that we just found, and we need to set it equal to 1/2. Take the natural log of both sides, so you get negative m over 5 equals the natural log of 1/2. I am going to multiply both sides by a negative 5, which will allow me to say that m is equal to negative 5 times the natural log of 1/2, which is the exact answer of the median, and that would be approximately 3.47 minutes. So while the averages claim to be 5 minutes, this actually shows you that they're kind of overdoing their average. The median actually is 3.47, so half of the customer's calls are actually answered in less than 5 minutes by a long shot. So that ends the video for section 8.5. That also ends material for this Calculus 2 class. So there are no more new videos after this one. So hopefully you enjoyed all the lectures.